Hello dear students, welcome you all. In this lecture, I am going to discuss about the deviation from the state of maximum probability, right? Deviation from the state of maximum probability, right? So, in this article, we are going to discuss this deviation. But very important thing is here we are considering the case of the distribution of n particle in two compartments, right? That we have discussed in the earlier lecture, right? We have two compartments and we are distributing n particle and distinguishable particle. This is very important. Distinguishable particle, right? In two compartments. So we have derived the expression for the probability of a macro state r n minus r, that was n factorial divided by r factorial into n minus r factorial into 1 upon 2 raised to power n, right? So here we have derived the expression for the probability of this macro state, right? And we have also derived the case of maximum probability p maximum. It was n factorial upon ny 2 factorial whole square into 1 upon 2 power n, right? So here in this article I am going to discuss how this system, right, behaves when I slightly deviate from this state. What is the state? The state is ny2 ny2 means 50-50 particles in one and 50% particle in number two compartment. So if I slightly deviate from it, right, if I make it 49 51, then I want to see what is the probability of a new macro state, right? So I'm going to discuss all this in this article, and at the end of this derivation we will learn that this system always try to remain in the state of this distribution 50-50. If we want to go away from this state, then the probability decrease rapidly, right? So we will start right from here, right? P maximum is equal to this, right? Now let be deviated slightly from this state of ny2 ny2, and I took a new state, right? That new state is a ny2 plus x, right? And the second one is a ny2 minus x, right? So now this is the new state, right? That I told you here, 49 51. So I want to see that what is the probability of this new state, right? And how it is linked with the maximum probability, right? So for it, now I'm writing the probability of the new state, that is p x is equal to n factorial divided by ny2 plus x factorial into ny2 minus x factorial into 1 upon 2 raised to power n. So what I am going to do? I am going to multiplying ny2 factorial square and dividing by the same factorial square. So what it will become? So I can write it as this thing n factorial, this whole term, right? This whole term is what? You can see here. This whole term is what? It is P maximum. You can see here it is n factorial divided by n by 2 factorial square into 1 upon 2 raised to power n. So it becomes now px is equal to p maximum into ny2 factorial square divided by ny2 plus x factorial into ny2 minus x factorial, right? So this is now the probability of this new state, right? This state, macro state, in terms of P max, right? So now my task is to solve this entire equation, right? So to solve it, what I will do? I will take the log on both the sides, right? Then after I will apply the Stirling formula. So taking natural log on both the sides, log of Px is equal to log of P maximum plus 2 log of ny2 factorial, right, minus log of ny2 plus x factorial minus log of ny2 minus x factorial. So what I did, I simply took the log, natural log on both the sides. So it become log of px, log of p maximum, multiplication. It is multiplication here. So it becomes plus, right? This 2 comes here, 2 log of ny2 factorial minus this, right? So now this is the uh, log. Now what I will take? I will take the Stirling approximation. That is log of n factorial is equal to n log n minus n. We are applying Stirling formula because here in this particular case, n is a very large, right? So when we will apply Stirling formula, right, to all the terms that contain factorial, then I will get in the next step. So when I apply Stirling formula, this side will become log of P maximum plus 2 log of ny2 factorial means ny2 log of ny2 minus ny n log n minus n, right, minus ny2 plus x log of ny2 plus x minus ny2 plus x, ठीक, n log n minus n, right? Similarly, minus bracket ny2 minus x log of ny2 minus x minus ny2 minus x, right? So this is what I got after expanding it through the Stirling approximation. So in the next step, I will get log of P maximum plus n log of ny2. I'm taking this 2 inside minus n, right? Then minus ny2 plus x log of ny2 plus x minus plus ny2 plus x, right? Here then minus ny2 minus x log of ny2 minus x minus plus ny2 minus x, right? So you can see here it is ny2 plus x and it is minus x got cancelled, ny2 and ny2 it is n, so it is again n got cancelled with n. So in the next step I am left with the log of p maximum plus n log of n by 2 minus n by 2 plus x into log of n by 2 plus x minus n by 2 minus x log of n by 2 minus x, right? So I'm left with it, right? Now in the next step, what I will do, I will take n by 2, I will take common here outside the bracket some terms, then this equation will get changed. Log p maximum, right, plus n log of n by 2, right, minus. Now here I want to n by 2 plus x. I want to simplify this term inside the bracket. So for it, I will take n by 2 common, right? So it will become, sorry, I should take log first. Log of n by 2 into 1 plus 2x upon n, right? Similarly, minus n by 2 minus x, right, into log of n by 2 into 1 minus 2x upon n, right. So this is what I got after taking n by 2 common in both these equations, right. So in the next step, it will become log of p maximum plus n log of n by 2 minus n by 2 plus x bracket log of n by 2 plus log of 1 plus 2x upon n, right. Similarly, minus n by 2 minus x into log of bracket n by 2, right. Not here, it should be bracket. I get mistaken. Here it should be bracket log of n by 2 plus log of 1 minus 2x upon n, right. So I got these terms after expanding this, right. So now I want to apply the Taylor's theorem, right. So Taylor theorem is basically log of 1 plus x is equal to x minus x square divided by 2 plus x cube divided by 3 minus so on. So and in case of 1 minus x, it is a minus x square divided by 2 minus x cube divided by 3 so on. So in this particular case, we are going to retain only to the second term, right. I will show you why we are doing so. When we will take the this Taylor's theorem, right, we can see we have the term here log of this and log of this. So it this first term log of 1 plus 2x upon n. So it will become here x is what, 2x upon n minus 2x upon n square divided by 2 means I can write 1 by 2. So you can see here why I said we will retain the terms only up to the second term, because here it is x upon n. So as x is very small as compared to n, I have stated in the beginning that this deviation, right, this deviation is extremely small as compared to n, right. So here if I took the cube term, then x upon n is again become very small, nearly to the zero. So we will retain only up to the second term. Similarly, log of 1 minus 2x upon, clear, it will give me minus 2x upon n minus 2x upon n whole square into 1 by 2. So what I will do, I will put these two values here and this value here, right? So when you will put these values here, you will get uh, log of p maximum plus n log of ny2 minus ny2 plus x bracket log of ny2 plus 2x upon n minus 2x upon n whole square into 1 by 2, right? Minus ny2 minus x bracket log of ny2 minus 2x upon n minus 2x upon n square into 1 by 2, right? So all these terms are written here. Now we'll try to simplify this equation. So sorry, when you will take the square, it will become 4x square upon n square. So 2 will get cancelled. So I can write here simply 2x square. Similarly here, it will become minus 2x square upon n square, and here it will again become minus 2x square upon n square, right? So now in the next step, I will again solve this equation. So in the next step, you will have log of p maximum plus n log of n by 2 minus n by 2 into log of n by 2 plus 2x upon n minus 2 x square upon n square. We are now multiplying these two factors to this minus x into log of n by 2 plus 2x upon n minus 2x square upon n square. This is first term. Similarly, for the second term, we will have minus n by 2 log of n by 2 minus 2x upon n minus 2x square upon n square, right? And minus minus plus plus x into, right, it will become log of n by 2 minus 2x upon n minus 2x square upon n square, right? So when you will take the things common, n by 2 is common here, so you can take n by 2 common. I'm doing it here, right? So I can write it in this way. I'm extending this bracket up to this. So you can see the terms, this will get cancelled with this, right? You will get a log of p maximum plus n log of n by 2 minus n by 2 bracket log of n by 2 plus log of n by 2, right? You will get log of n, clear? Similarly, in this case, when you will take multiply the x inside this bracket, it will become minus x, it will become plus x, right? log of n by 2, they will get cancelled out. Similarly, when you will multiply it, it will become minus 2x square, right? So it will again get cancelled out, right? So this thing, and it will become minus, sorry, it will not cancel out because it will become minus, clear, and x will be multiplied, obviously, minus 2x square upon n. We will get a term minus 2x square upon n. Similarly, here we will get minus 2x square upon n, right? And when you will multiply this with this, it will become plus 2x cube upon n square. It will become again minus 2x cube upon n square. So they will get cancelled out, right? You can see here minus minus plus 2x cube upon n square plus, as it is minus, so that they will get cancelled out. So these terms will get cancelled out. So here in this first equation, I will get minus 4 x square upon n square also, right? So here I think I have mistaken here. Log of n by 2 plus log of n by 2, it will become 2 log of n by. So when I will multiply it, I will get log of p maximum plus n log of n by 2 minus n log of n by 2 plus 2 x square upon n, right, minus 4 x square upon n, these two terms, right? So this got cancelled. I am left with the log of p maximum, right, minus here it was sorry, plus 2 x square upon n minus 4 x square upon n, right? This is what? This is log of px. So this is the required probability. So I can rearrange, I can take this to this side. It will give me log of px upon p max, right? That will be equal to 2x square upon n minus 4x square upon n, right? When I will simplify, it will give me minus 2x square upon n toward this side, right? So it will become minus 2x square upon n, right? So if I further simplify it, I takes the logarithm on both the sides, sorry, exponential, then it will give me px upon p maximum is equal to e raised to power minus 2x square upon n, right? I can write it further, e raised to power minus ny 2 into 2x upon n square, right? So I wrote it in order to write this term 2x upon n is equal to f. Fractional deviation, I can write this as a x divided by n by 2, clear? It will ultimately give me this 2x upon n. So what is, I actually wrote it in this way in order to express this exponential factor in terms of this fractional deviation. X upon n by 2 means x upon 50%, means how much deviation we have made. So I will give this a name f, fractional deviation. So in that case, it will become e raised to power minus n by 2 into f square, right? Px upon p maximum, right? So I can write px is equal to p max into e raised to power minus n f square divided by. So this is the required expression for the probability of a new state, that is fractionally deviated from the most probable state, right? So now I am going to do the analysis of this relation. This is equation number 1. This is the result of this entire discussion, entire mathematics that we did during this entire article. So now I'm going to make the analysis, right? How this px will change as we will make the change in the value of n and f, right? So to do the analysis, let's consider a particular case where uh, n is equal to 10 raised to power 6 particles, and the fractional deviation is of the order of 0.1%, right? 0.1% means it is a 0.001, right? Because 0.1% will give you 0.1 means 1 upon 1000, right? So I can write it as 10 raised to power minus 3. So f is equal to 10 raised to power minus 3 means 0.1% deviation from the state of maximum probability. N is equal to this. So if I put the value px is equal to p max into e raised to power minus ny. N is 10 raised to power 6 into uh, f square. F square means 10 raised to power minus 3 square means minus 6 divided by 2. Right. So it will give me 10 raised to power 6 minus 6. It will give me 10 raised to power 0. So it will give, it was also negative there. So it will give me p max into e raised to power minus 1 by 2. So if I put the value of e raised to power minus 1 by 2, it is 0.607 p max, right? So this is the first case when the number of particle is equal to this. Now let's see what happened when I increase the number of particles, right? Let instead of 10 raised to power 6, we have n is equal to 10 raised to power 9. Let's see what happened here. In that case, it will become p maximum into e raised to power minus 10 raised to power 9 into 10 raised to power minus 6 divided by 2. So it will give you p max into e raised to power. Now here it is 10 raised to power 9, 10 raised to, it means 10 raised to power 3, 1000 divided by 2, e raised to power minus 500. So it will give me p maximum upon e power 500. So you can see here that this number is very small as compared to this number, right? Means the probability of the new state px becomes even more smaller, right? It decreases rapidly, exponentially. Let's take the another case, right? When n is equal to 10 raised to power 12. So obviously, if I put 10 raised to power 12 here, it will increase zeros in the denominator, and I will get a 3 more zero, right? Means I will get a probability of x is equal to p max upon e raised to power 5, right? So this is the probability of the new state, because here I will get 10 raised to power 12, so 10 raised to power 6, right? 10 raised to power 6 divided by 2, so I will get this number, right? So you can see the difference as the number of particles increase in the system. The deviation, slight deviation 0.1% is rarely possible, right? It means system always try to remain in most probable state, the state in which there are 50-50 chances for both the compartments having equal number of particles. I mean 50% particles will be in one compartment and 50% particles will be in two compartments. If I plot a graph, right? Let's plot a graph. So it is the vertical axis. Let this is the horizontal axis, right? We are taking along this direction, we are taking uh, px upon p maximum, or I can say simply px. You can write it in this way also, px, the probability of the new state, right? And here in the uh, horizontal axis, you are taking the fractional deviation, both the sides, right? So it is uh, zero point 0.1, it is 0.2%, it is 0.3%, it is zero point 0.4. So similarly here, the same thing, 0.1, zero point 0.2, zero point 0.3, zero point 0.4, right? Because one thing that is of importance here, f is equal to like zero point 0.1, zero point 0.2 I took. If I took negative zero point 0.1, all that, they will make no difference, because in the same, because here it is a f square in the expression, so it will make it positive. So what we will get, we will get a graph of you right, right. This is the way you will get, right. What does it show? It show that as we, this is the case of 0, when the fractional deviation is 0, the probability is equal to p maximum. So as you go either toward this side or toward this side, this is let for n1, this is for n1, this is for n2, this is for n3, right? And n1 is greater than n2, it is greater than n3, right? So you can see here that as we go away from the state of maximum probability, right? That is fractional deviation is 0, the probability of the new state fall off exponentially, right? And it falls off more rapidly when the number of particles are large. As n1 is large, so you can see the graph is very narrow, right? N2 is small as compared to n1, so you can see the graph is little wider. Similarly, in case of n3, it is more wider. So it is clear that as the number of particles are large, then in that situation, there are very low chances of the fractional deviation from the state of maximum probability, right? So I think this discussion has cleared the motive of this article, and all the things are clear. We have derived the formula. This is an important topic in statistical and thermal physics, and usually asked in the examination. So we have to do all this exercise up to this point with the examples, right? So thank you very much.